In frequency response analysis, you will get the questions on three different topics. One is polar plot, one is Bode plot, and one is Nyquist plot. Polar plot is optional because Nyquist plot is extension of a polar plot only. So today I will start with the polar plot. In tomorrow's class, Professor Anand Kulkarni will complete the Bode plot. So before coming to the class tomorrow, all of you have to buy some 4-5 what is known as semi-log sheets. Semi-log papers, you will get it in a market, and preferably by inch scale. Centimeter scale is also available, but which is not very common. By inch scale only, because in your answer sheet, whatever semi-log paper is provided with the answer sheet, it is in inch scale. So there are one semi-log paper provided to you in the answer sheet, and as far as possible, you are not supposed to refer to any supplements. So only one question will be there most probably in Bode plot, which has to be drawn on semi-log inch scale. So semi-log means on one side log and one side normal scale will be there. So if you go to the market, A4 size sheets you will get. Buy some number, 8 to 10 number, because you have to practice those problems in your home also for your preparation. So for polar plot, what I am going to cover today, you can draw it on a normal answer sheet also, or you can draw it on a graph sheet which is provided in the answer sheet. So option is yours. It is not compulsory. Graph sheet is not compulsory. Like a root locus. Root locus also can be drawn on normal answer sheet paper, plain paper, or you can draw it on a graph also. The option is yours. It is not mandatory. But for Bode plot, you have to use the graph sheet only. So today we'll start with the what is known as frequency response analysis. So basically, so far whatever we have covered in the class is that is in unit number 3, that is route stability criteria, time response analysis, and root locus technique, which are part of what is known as time response analysis. That means you are going to plot the graph of output of the system C versus time. And it is also called as transient response analysis, because here you are taking the response as time t tends to infinity. That means below infinity it is plotted. So whereas the frequency response analysis, here you are going to plot the graph of output versus frequency, not versus time. And moreover, it is called as steady state response. Steady state response is, that means after time t tending to infinity here also, as not time t, omega tending to infinity here also. So it is steady state response. So time is not a variable here, whereas frequency is the variable, whereas and you are going to see the output of the system. So this is regarding frequency response analysis. So in the frequency response analysis, what you are going to do in time response analysis, what you are used is, you have used some transient inputs. Like you have used step input, ramp input, parabolic input, and impulse input. Whereas in the frequency response analysis, you are going to use a sinusoidal wave. So R of t, in earlier case, it is step input is 1, impulse input is delta t, ramp input is t, whereas parabolic input is t square divided by 2. Whereas here, input R of t, if you see here, is A sine omega t, where A is the amplitude of the sine wave and omega is the frequency of the sine wave. You can see the smaller wave, which is
Hello, sir.
the amplitude is A and its frequency is omega. Whereas now, if r of t is A sine omega t, then r of s, that is after taking the Laplace transform of sine omega t, it becomes omega divided by s square plus omega square, whereas A is the amplitude, it gets multiplied with that.
Sir, your screen sharing is off.
On.
Now it is clear?
Yes.
Ah. So here you can see A sine omega t is the input, where A is the amplitude of the sine wave and omega is the frequency of the sine wave. If you take a Laplace transform of r of t, it becomes r of s, which is A remains as it is into omega divided by s square plus omega square, that is the Laplace transform of sine omega t that we have studied in time response analysis earlier. That now here if you put r of s is equal to a omega into s square plus omega square, and c of s can be written as r of s into g of s. G of s I have kept as it is, whereas this is a sine a into omega divided by s square plus omega square. Now to get c of t, I have to do partial fractions like a time response analysis. I will write two partial fractions for s square plus omega square as s plus j omega into s minus j omega. See, s plus j omega into s minus j omega becomes s square plus omega square. Reason is s plus j omega into s minus j omega, that is a plus b into a minus b is a square minus b square, that is s square minus j omega whole square. J omega whole square, j square becomes minus 1. So it becomes minus of minus plus. So s square plus omega square can be written as s plus j omega into s minus j omega. So A is the amplitude as it is, I have taken outside the bracket, whereas B is one partial fraction. So B upon s plus j omega plus C upon s minus j omega. Remaining partial fractions for the poles and zeros of g of s, I am going to write the partial fractions d divided by s plus a, e divided by s plus c, b, f divided by s plus e, so on. You can write depending on the number of poles for transfer function g of s. That is not important here, because after evaluating the partial fractions, you will come to know that this whatever is the value of d, e, whatever it is going to be multiplied by e to the power minus at, e to the power minus bt, e to the power minus ct, depending on this value of the pole. And as time t tends to infinity, because as said, it is a steady state analysis. When it is steady state analysis, time is tending to infinity. When you put a time t into as infinity, then in this case, anything to the power minus infinity is 0. So all these terms vanish, whereas these terms will remain. Only that sine omega terms will remain. And if you take the inverse Laplace, it will become x, where amplitude gets changed, or b, x or capital B into sine omega t plus phi. That means when any given system is subjected to a sinusoidal input, output is also a sinusoidal output. Output is also a sine wave. Only thing, its amplitude will either increase or decrease depending on the values of these partial fractions, and frequency will not change. Frequency will remain same only. What will change is either phase lag will be there or phase lead will be there. Either, that means the output wave which is shown over this either lags the input or leads the input by angle phi. Now here whatever is shown is lagging. It is lags by amount equal to phi. So that means the input wave starts before and output wave starts with certain gap. If the output is leading the input, it starts before the input wave. That is called as phase lead. So phase lead is normally which is not present in stable system. Only phase lag will be there in the stable system. Phase lead will not be there in most of the stable systems. So we generally don't bother about it. So that means here the analysis becomes very simple. Reason is, if you see the time response analysis, for first order system there is a separate time response, second order underdamped separate, overdamped separate, critically damped separate, third order once again 3-4 different types, fourth order, it goes on. It is practically impossible to analyze the time response analysis for higher order systems greater than second order system, and because of the complexity involved. Whereas in frequency response analysis, the advantage is the response is always fixed. You know the type of response. That means if the input is sine wave, output is also a sine wave of same frequency. The frequency remains same. Only thing is its magnitude changes, and either there will be a phase lag or phase lead. That is the so that's why the frequency response analysis is most commonly used analysis in control engineering. For stability analysis, time response analysis is very rarely preferred, whereas in most of the cases we end up in doing only the frequency response analysis. If the frequency response analysis gives you stable output or stable system, generally the time response also gives the similar result. Only thing, for design purpose you have to use the root locus technique. Otherwise, if it is not a design, only analysis is to be performed, in then generally we end up in doing only by what is known as frequency response analysis, because it is very easy. And in the frequency response analysis, you have two options: either to do the Nyquist plot or to do the Bode plot. By both the plots, you can determine the stability. Whereas polar plot doesn't give you stability, but it will give you the idea about the system stability little bit. So polar plot is actually the beginning of the Nyquist plot. So unless you have a background of polar plot, you cannot plot the Nyquist plot. That's why we are covering the polar plot here. In some of the books, polar plots are missing, only Nyquist diagrams are discussed. Reason is, polar plot is not commonly used for analysis purpose. It is just for understanding, so that you can easily draw the Nyquist plot. So here what we can see is that first we'll see how to draw the polar plot. So what thing you have to remember in the frequency response analysis is that as time t tends to infinity, it is a steady state analysis, whereas time response analysis is time t below infinity, and hence it is transient analysis. That is the major difference. Another thing is, in time response analysis, you have to use either route stability criteria to determine the stability, or to use the root locus technique to further analyze the system. Whereas in frequency response analysis, you are subjecting the system to a sinusoidal input, and the output is also a sinusoidal wave. Only difference is its magnitude or amplitude will change, and phase angle will be there. That means either phase lag or phase lead will be there. Frequency doesn't change. That is what is the important. So this is regarding the basic idea about the frequency response analysis. Then we can go for what is known as polar plot. See, the polar plot, are the name indicates it is in polar coordinates. The polar coordinates is in r theta form. It is always expressed in r theta. So in root locus, we have used the Cartesian coordinate systems, that is x and y, where x is the real part and y is the imaginary part. So to plot any given point, just see here in a root locus, what we have done, to identify this z, you have to measure x along x-axis, that is real axis, whereas y along y-axis, that is vertical or j omega axis. So here there is a mistake. I have written y-axis here and x-axis here. It is not. This is x-axis, normal x-axis. This is y-axis only. So x coordinate has to be measured along y-axis. Y coordinate is measured along y-axis or j omega axis, and you locate the point z there. So this is in Cartesian coordinate. In polar coordinate, what you have to write is z is equal to, what is z? This distance, that is the diagonal distance from origin. From origin, you have to connect the diagonal to point z. This length of this diagonal, as per the Pythagoras theorem, is x square plus y square under root. So this is called as, z is called as, here now this root of x square plus y square is called as magnitude. It is called as magnitude. And only by measuring this, you cannot plot the point. Only one value will not be sufficient. You come to know this distance, you come to know the distance, but you can't know the location of the point z. Whether it is on this side, this side, this side, we don't know. So you require one more thing, that is called as phase angle or phi. That phase angle is given by tan inverse of opposite side upon base, that is y upon x, or that is imaginary coordinate divided by real coordinate. Imaginary coordinate divided by real coordinate. So another difference is to identify that we are going to plot the polar plot. That means plot in the polar coordinates. So the axis name is also changed. In root locus, we call this x-axis or horizontal axis as called as sigma axis. It is called as sigma axis, whereas y-axis, we don't call it as imaginary axis, but it is called as j omega axis. It is called as j omega axis. Omega value will be taken along the y-axis and the real part is taken along x-axis. So it is in Cartesian coordinate. But in polar plot or in a polar coordinates, we will call x-axis as real axis. And also the angle of this real axis is 0. Angle of the real axis is 0. Whereas if the angle is measured in a counterclockwise direction, so y-axis is called as imaginary axis and this becomes 90 degrees. This becomes 180 degrees. This becomes 270 degrees. This becomes 360 or 0 degrees once again. But if you measure the angles in clockwise direction, so this becomes minus 90 degrees. This becomes minus 180 degrees. This becomes minus 270 degrees. This becomes minus 360 or 0 degrees. So what happens is 180 degrees plus or minus is same line. 0 or 360 plus or minus is same line. Only thing is these two angles will change. If you measure in clockwise direction, it is minus 90. If you measure in anti-clockwise direction, it is plus 270. Whereas this axis is in clockwise direction, it is minus 270. In anti-clockwise direction, it is plus 90. That is what is the important. And only these angles and the magnitude is important for the polar plot. So coming next to what is known as a polar plot. So the example, this is the first example we are going to take. G of s is given as, the transfer function of the system is given as 1 upon 1 plus ts, where t is constant. It is like 1, 2, 3 or some number. Generally, it is constant. So first in polar plot, what you have to do is put wherever s is there as replace it by j omega. So wherever there is s is there is replaced by j omega. So g of s is replaced by g of j omega and 1 plus ts is replaced by 1 plus tj omega. So now you have to find out what is known as the magnitude. Magnitude is drawn with a double horizontal line. Only sign is positive there. Irrespective of sign, it will give you the value. So sign is not important here. So you can write the magnitude. How you have to calculate magnitude? Here it is shown. What is magnitude? Root of real part square plus imaginary part square. Real part square, imaginary part square. See here in the numerator only 1 is there. 1 is not imaginary, it is real only. So real square, that is 1 square, plus imaginary square, that is 0 square, under root. So 1 square plus 0 square is 1 square only. Under root of 1 square or 1 is 1 only. So the numerator becomes 1. Whereas denominator, if you see, the real part is 1, imaginary part is t omega, not j. J indicates it is imaginary. J need not have to be considered. So you need not have to square t j omega, so j square becomes -1. No. So you have to consider only the coefficients of j. Coefficients of j is t omega. So root of real part square, that is 1 square, plus t square omega square. T square omega square, not j square. So plus sign will be there under root of that. This is what is the magnitude. This is what is the magnitude. Whereas if you find out the angle of numerator minus angle of denominator, it is the equation. What is the angle of numerator? In the numerator only 1 is there. So what is the angle equation? Angle equation is tan inverse of y upon x, that is imaginary part divided by real part. That is imaginary part divided by real part. In the numerator there is no imaginary part. There is no imaginary part. So tan inverse of 0 divided by 1 or tan inverse of 0 is 0 only. So angle of numerator is 0 minus angle of denominator. So 0 I have not written here. Directly I have written minus. 0 minus tan inverse of imaginary part. What is imaginary part? T omega divided by real part, that is 1. So t omega divided by 1 or omega t. So tan inverse of omega t is what is known as angle with minus sign because it is in the denominator. So as far as the angles you have to consider, angles in the numerator gets added up with positive sign. Angles in the denominator gets subtracted from them because they are negative. So if you do this, afterwards, I will draw what is known as a polar plot. So this is the equation for magnitude. This is the equation for phase angle. So I will make the table. I will make the table here. I will put the value of omega, value of magnitude, value of angle. I have named those points. So you are going to plot in frequency response analysis. Omega has to be changed from 0 to positive infinity. 0 to positive infinity, 0 to infinity only. So the two end values I am going to consider. Two end values are starting value is 0, ending value is infinity for omega. If you put omega is equal to 0 in the magnitude equation, this is the magnitude equation, put omega is equal to 0, 0 multiplied by anything is 0, 1 is there, root of 1 is 1 and 1 upon 1 is 1. So the magnitude becomes 1 here. Whereas if you see the phase angle is given by the angle minus tan inverse of omega t. Omega is 0, so tan inverse of 0 is 0 only. So the angle becomes 0. Then the second value I will put. Second value is end value of omega. End value of omega is infinity. End value of omega is infinity. So put omega is equal to infinity in the magnitude equation. So if you put omega is equal to infinity, omega square, infinity square is also infinity, multiplied by anything is infinity, added by anything is infinity, and root of infinity is infinity only. So 1 upon infinity is 0. So the magnitude becomes 0 here. Correct? Then phase angle, you put omega is equal to infinity, tan inverse of infinity is 90 degrees. So minus sign is outside, so hence minus 90 degrees. So I have plotted the 2 points. So I have taken a real axis, I have taken an imaginary axis. On the see the first point is A point, I am plotting A point. A point is on 0 degree line, 0 degree is horizontal, real axis line, positive real axis line. because that depends upon the angle. Angle is 0 means this angle. This is 180 angle. So angle is 0 means this line. Magnitude is 1. It doesn't have any sign, positive sign only. So on this line you have to measure 1 unit from origin. From origin O, that is written as B here because B point coincides with the origin. So I have not written it as O, but it is same as B. So from O you measure 1 unit distance, whatever with the scale, and mark the point A. This is the starting point. Second point B is magnitude is 0, angle is minus 90. Which is minus 90 angle? Minus angle is measured in a clockwise direction, plus angle is measured in anti-clockwise direction. So you can see here, if you measure the angle in clockwise direction, this becomes minus 90, or it is 270 also. Plus 270 or minus 90 are same. So minus 90 angle if I measure, on this line I have to measure equal to the magnitude, that is 0. So 0 means it coincides with the origin. So that is point B. So we got A to B. So the plot goes like this. From origin it will start, it goes to A, and second point is B. So in between what happens? Is it a straight line plot or something different? For that I have to take some other point. As this is the first point, this comes under what is known as standard polar plot sections. So the standard polar plots you have to remember, which I will show you the sheet at the last, and you can easily remember them. There is a very easy thing to understand that we'll see later. So I will take the third point. I will take the third point as omega is equal to 1 upon t. It is called as corner frequency. It is also called as corner frequency. Omega is equal to 1 upon t, where t is the coefficient of that. So if you put in magnitude equation, omega is equal to 1 upon t. So 1 upon t square and 1 upon t square cancels here. You will get 1. So 1 plus 1 is 2. Root of 2 is root 2, and 1 upon root 2 you will get. So the magnitude will be 1 upon root 2. Whereas angle, if you put omega is equal to 1 upon t, t upon t cancels, so you will get 1 here. Tan inverse of 1 is 45 degrees. So tan inverse of 1 is 45 degrees, and minus sign is as it is there. So minus 45 degrees. So the third point I will take. So first measure minus 45 degrees. Minus 45 degrees means clockwise measurement. So you move this 90 degrees, go to 45 degrees, draw a line. On that, take a distance of 1 upon root 2. So this is 1, this is 1 upon root 2. 1 upon root 2 is 0.707. So 0.707, you measure it, you plot the point C. Now what happens is, see here, this is 45 degrees and this distance is 1 upon root 2. This distance is also 1 upon root 2. You can verify that because this distance is 1. So Pythagoras Theorem, 1 upon root 2 square plus 1 upon root 2 square under root is 1 only. So if this has to be 1, this has to be 1 upon root 2. So this angle also has to be 45. So this angle in a triangle is 45. This angle in a triangle is a 45, means this angle is 90 degrees. So it is nothing more than a semicircle, because angle in a semicircle is always 90 degrees. That you know from the school days in the geometry you have studied. So this becomes a semicircle. ACB is a semicircle. It starts at A and goes to B through C. So this is what is a standard polar plot. Is it clear to you? This is the simplest polar plot which is explained in any book. Almost all books they have explained this plot. And this is called as first order pole. 1 upon 1 plus TS is called as first order pole. This is a first order equation. If you remember the time response analysis, we have taken 1 upon 1 plus TS as the first order system transfer function. So this is called as first order pole because it is in the denominator. Then the second problem, I will take two poles in the denominator. I will take two poles in the denominator. So if I take two poles in the denominator, it is one pole is at origin. So there is one pole at origin, s is equal to 0, and one pole which is a first order pole, that is at minus 1 upon t. So there are two poles, one at origin, one at first order pole. So if I add, I want to study the effect of, if I add one pole at origin to a first order system. If I add a pole at origin to a first order system, it becomes a second order system now, because there will be two poles and a square term is bound to come. So first thing what I will do is, I will put s is equal to j omega, and I will write, wherever s is there, I will write j omega, and this is 1 plus tj omega. I will write like that. Now I will write the magnitude. Magnitude of the numerator, as 1 is there, root of 1 square plus 0 square under root. Real part square plus imaginary part square. There is no imaginary part in the numerator. So 1 plus 0, 1 square plus 0 square under root is 1 only. Whereas this I will separate. I will separate this and this. What is j omega? J omega is imaginary. So 0 plus omega square under root is omega only. 0 plus omega square under root is 0, omega only. So 0 plus omega is 0, omega square will be there, root of omega square is omega. So that as it is. Whereas this we have already studied. So the previous problem only, real part square, that is 1 square plus t square omega square under root. 1 plus omega square t square under root. That I have written. Now angle. Angle of the numerator real is there. So tan inverse of imaginary part, that is 0 divided by 1 is 0. So 0 is there, minus this part angle. See this angle. Angle of j omega. Angle of j omega, tan inverse of imaginary part divided by real part. Imaginary part is omega, real part is 0. So tan inverse of infinity is minus 90. So minus 90 will be there. No, it is plus 90, but it is in the denominator, so minus 90. So one angle is minus 90. And this angle you already know in the previous problem. Tan inverse of imaginary part, omega t, divided by real part 1, that is omega t. So this is the magnitude equation. This is a phase angle equation. So we'll take a 15 minutes break and we'll continue with the problem. Any questions are there so far? Because these are simple problems. These simple problems with value of t asked number of times in the exam, and they are called as standard polar plots, and they will come not more than 5 marks, for not more than. There are some more complex standard polar plots are there, which will come for 10 marks or 15 marks also, but these simple ones will come for max 5 marks. So have you understood how to plot that? First
Yes,
question.
sir.
So
Hello,
we'll
sir.
take a break and we'll meet.
Hello,
Doubt
sir.
is there?
Yes, sir. Sir, how to calculate the phase angle, sir? Equation. Once
What?
again.
Second problem.
Second problem, sir.
Oh. I repeat. What is phase angle? Angle of numerator minus angle of denominator. Angle of numerator. In the numerator, 1 is there. In the 1 is tan inverse of imaginary part divided by, angle is tan inverse of imaginary part divided by real part. Imaginary part is 0 in the numerator. So 0 divided by anything is 0 only. So tan inverse of 0 is 0 only. So angle of numerator is 0. Even this, instead of 1 you have some number also, say k in general. Then also it will become 0 only, because imaginary part is 0. Unless there is an imaginary part in the numerator, the angle will be 0 only. So the angle of denominator, minus you have to do. So minus, say j omega is there. These two terms you have to separate. You are not supposed to multiply them. You are not supposed to multiply them, because the angles will go on getting algebraically added. The multiplication becomes addition and division becomes subtraction. So this is the principle of log also. That's why we are using a semi-log sheet in a Bode plot. So the advantage of using a log is addition becomes multiplication becomes addition, whereas division becomes subtraction. That is, a into b becomes a plus b. Log of a plus log of b is equal to log ab. Correct? Whereas similarly, log of a by b can be written as log of a minus log of b. This is a formula. So multiplication becomes addition and division becomes subtraction. So now this is multiplication here, so it becomes algebraically added. Whereas this is subtraction because this is numerator minus. So this minus sign is allocated for denominator, plus sign for the angle is allocated for numerator. So angle of j omega plus angle of this we have to do. So angle of j omega is tan inverse of imaginary part is omega divided by real part is not there for j omega because there is no real term along with this. So naturally it is 0. So tan inverse of omega divided by 0 is tan inverse of infinity. Tan inverse of infinity you know is 90 degrees. As it is in the denominator, it is minus 90 degrees. Similarly, tan inverse of imaginary part, that is t omega for this, divided by real part, that is 1, that becomes t omega only. So tan inverse of omega t I have written. Is it clear now?
Yes, sir.
Okay. We'll take a break now. We'll complete this problem in the next class.